Hello everyone, I hope everybody is doing great and you are fit and fine. So I welcome you all to the fourth amazing session of the general organic chemistry. So here we go students, let me start the first question. The correct order of resonance stabilization for acid chloride, ester and acid amide. These are the collective functional groups which are called as acid derivatives. Why are these called as acid derivatives? Because they have been derived from the carboxylic acids. Now, we have to compare the order of resonance stabilization for each of the compound. Let us see, students. So we have acid chloride. For acid chloride, we have Rc double bond OCl. So here we have lone pair pi conjugation. The 2p orbital of carbon and 3p orbital of chlorine will involve in resonance. When you have two different type of energy shells involving in the covalent bond formation, whether it is a sigma bond or pi bond, definitely it will be a weak. So definitely in this case, the resonance stabilization won't be that great. Let us have a look similarly on the other functional groups. Like here we have ester, Rc double bond O, OMe, where the lone pair on the oxygen will involve in resonance because it has lone pair pi conjugation. So here you have 2p orbital of carbon, again here 2p orbital of oxygen. But when you compare 2p orbital of carbon and 3p orbital of chlorine and 2p orbital of carbon and oxygen, definitely ester will have better resonance stabilization, right? Next, we have amide. So when you go for amide, Rc double bond O NH2. So in that case, here also you have actively lone pair pi conjugation for 2p orbitals of carbon and 2p orbitals of nitrogen. Then how do you compare that nitrogen can efficiently donate its electron pair or oxygen can efficiently donate its electron pair? What is the relation between nitrogen and oxygen? They are a part of the same period. When they are a part of the same period, electronegativity predominates. Oxygen, being more electronegative, cannot actively involve in resonance as that of nitrogen. In that case, amide will be the best, followed by ester, followed by acid chloride. So in that case, we have to choose which option. First, we need to have amide, ester, and acid chloride. That is option C. I hope the concept is very clear. Great. Let's move to the next question, guys. Which among the following molecules have unique carbon-carbon bond length? See, this is question based on aromaticity. Instead of asking you to identify the nature of the compounds, whether it is aromatic or non-aromatic or anti-aromatic, he has put the question the other way around. Because in case of aromatic compounds where you have a continuous delocalization, where you have an alternate pi bond system or alternate charge-based pi bonded system, you will have a continuous delocalization. In that case, what happens? You will have a partial double bond character. When you have a partial double bond character generated within the ring, you cannot have absolute bond length similar to that of carbon-carbon single bond or carbon-carbon double bond. So whenever you have aromatic compounds or quasi-aromatic compounds, they are known for their unique feature having a distinct carbon-carbon bond length, which we consider as a partial double bond character. It is not similar to that of a pure single bond or pure double bond. It is in between carbon-carbon single bond and double bond, which we call it as partial double bond character. So, which among the following molecules have unique carbon-carbon bond length? First one is a 7-membered ring, which is troponium carbocation. It is a 6 pi electron system. With 6 pi electron system, it can actively involve in resonance, thereby having aromaticity. So this is aromatic compound. This is benzene, and this is also an aromatic compound. And now this is a derivative of a squaric acid where you have the negative pi conjugation with having 2 pi electron system in the ring, where due to the positive charge created due to the presence of carbonyl group, these 2 pi electrons can actively involve in resonance. So this is also aromatic. And now we have another example having 8 pi electron system, which is anti-aromatic. Isn't it non-aromatic when you have 8 pi electron system? Is it anti-aromatic? No. This is not anti-aromatic. With 8 pi electron system, actually it has to be anti-aromatic, but it is non-aromatic. Why it is non-aromatic? Because it won't have continuous delocalization. With 8 electron system, with cyclooctatetraene, what is the problem here? The problem is the loss of conjugation. Remember, for conjugation, minimum 3 orbitals, that is 3 p orbitals, should be lying on the same plane. Then only conjugation is applicable. But here what happens? These 2 p orbitals are on the same plane, but the other p orbital is perpendicular. Again, these p orbitals are on the same plane, and the other 2 p orbitals are perpendicular. So in this case, do you expect? No. So what is the final answer, guys? So we have tropyl carbocation, benzene, and square anion. That is option A, B, and C are the molecules having unique carbon-carbon bond length. I hope you have understood this. Great. Let's move to the next concept. Which of the following options are correct? Let's see this. Which of the following combinations are correct? First one is asking for the acidic strength. For the acidic strength, how do you compare the strength of an acid? It is based upon the stability of the anion. K is directly proportional to stability of anion. It is based on anion stability. So this is, we have 1, 2, 3, 4. Again we have 1, 2, 3, 4. So this is cis but-2-enoic acid, and this is trans but-2-enoic acid. Cis and trans are geometrical isomers. In this case, after releasing H plus ion, the corresponding carboxylate ion is more stable. When it is more stable, the acidic strength relation stands true. So the first option is correct. Now let us compare the second one, free radical stability. This one, in the first option you have the radical which is formed here. It is attached to 3 different carbons, so this is tertiary free radical. Tertiary free radical with how many alpha hydrogens? This is 1 alpha carbon, this is 1 alpha carbon, this is 1 alpha carbon. 3 plus 2, 5 plus 2, 7. So we have total 7 alpha hydrogens. So with 7 alpha hydrogens, it can actively involve in hyperconjugation, right? Next, this is conjugated lone pair, not lone pair, sorry, odd electron pi conjugation. When it is odd electron pi conjugation, it can actively involve in resonance. This has to be more than this. Yes. And the next one you see, you also have the same condition, that is odd electron pi conjugation. So in the second one also you have odd electron pi conjugation, but you have more extended conjugation. Greater the number of resonating structures, greater will be the stability of the reaction intermediate. So in that case, the order is correct. So option B also stands true. Is that? Chalo. Let's move to the third one. Basic strength. For acidic strength, the stability is based on the anion. For basic strength, the stability is based on the stability of cation. Let us understand. After accepting the H plus ion, because this lone pair is also equally available, this also lone pair equally available. sp2 localized, the other case also sp2 localized. So by accepting H plus ion, nitrogen gets a positive charge, so this can involve in hydrogen bonding. So the solvation ability when it involves in hydrogen bonding increases. When it increases, the cation stability increases. But here you can't really expect. You can't have hydrogen bonding when this nitrogen accepts lone pair. So the relation stands true. So option C is also correct. Now come to option 4. In the fourth one is asking you to compare the acidic strength. Here we go. Here also the same thing. Once it releases H plus ion, you will have CO minus. Here you have C double bond OH. So do you think that the hydrogen atom here after releasing H plus ion, you will have something like this, right? C double bond O minus. Or you can take here you have C double bond O minus. This O minus and this positive charge. It can have ionic interaction. When it is having ionic interaction, the cation is getting stabilized, the intermediate is getting stabilized. But can you expect to have such stability when you have CO minus and NR3 plus being at the opposite end? Then this relation is also stands true. So all the 4 options are correct in this particular question. Is that clear? So definitely guys, in this type of questions, when you have multiple concepts in a single question, now these are the current trend. These are the current trend. And one more thing students, I'm very proud to tell you that one of my student, Master Mukund Kakodkar from Goa, has scored full marks in organic chemistry and inorganic chemistry for JEE Advanced 2023. I'm really proud of you, Mukund. So the reason why I am highlighting his name and his achievement, so that all of the students who are watching this video, you should also get equally motivated. Inorganic chemistry can also be crammed, students. Let me tell you, inorganic chemistry, once you properly deal with concepts, then you can easily master over it like organic chemistry. Only thing is that inorganic chemistry has put under a wrong marketing that inorganic chemistry कुछ नहीं है, उसमें सिर्फ रट मारना है, उसमें कोई concepts नहीं है. This is very very damn wrong, students. I strongly condemn this. Even inorganic chemistry also, if taught properly with proper concepts, even inorganic chemistry can also be achieved at the master level. Right? Come on, let's move to the next thing. Which of the following statements is correct? The relative nucleophilicity in aprotic solvent is given in the order I minus greater than Br minus greater than Cl minus greater than F minus. Aprotic solvent. What do you mean by aprotic solvent? Where there are no active hydrogens. Like you have acetone. This is polar aprotic solvent. Polarity is due to the presence of C double bond O group. But there are no active hydrogens. How do you know whether there are active hydrogens present or not? If hydrogen is attached to a highly electronegative element, like say suppose sp carbon or nitrogen or oxygen or halogen, then they are considered to be active. Like water is polar protic solvent, acid polar protic solvent, acetone, DMSO, all those are aprotic solvents. And is asking you to compare the halide ion nucleophilicity. What do you mean by nucleophilicity? Ability to donate an electron pair to the electron diffusion center. Where when you tell it is a nucleophile, it is always going to attack at the electron deficient carbon. So How do you compare? As it is a polar aprotic solvent, anion does not get stabilized through hydrogen bonding. There is no solvation effect. When there is no solvation effect, it depends upon the size. Smaller size of anion will have greater electron density. When the electron density is high, ability to donate will be more. So what will be the exact order? Fluoride, chloride, bromide followed by iodide. So the order will be F minus greater than Cl minus greater than Br minus greater than I minus. So the first one, the order will be incorrect. The relative order of minus I groups is NF3 plus greater than NH3 plus greater than NR3 plus greater than NO2. Is this relation correct? NF3 plus, nitrogen having a positive charge with halogen, NH3 plus greater than Ne3 plus. Is it? Let's see. Usually when you have NMe3 plus or NR3 plus and NH3 plus, you will have a strong repulsive action between the alkyl groups. Due to the strong repulsive action, what happens? Their bond angle increases. When there is an increase in the bond angle, what happens to the electronegativity? Electronegativity increases. When you have like percentage of S character, in case of percentage of S character, the space occupied will increase and its bond angle increases and electronegativity also increases. When electronegativity increases, the ability to withdraw the minus I power will be more. So Nr3 plus will have more than NH3 plus. You cannot compare the nature of electron releasing nature of methyl group attached to the nitrogen, because due to a strong repulsive actions they will move far away. Inductive effect is always driven by distance based. So once there is a huge change in their bond length, what happens? Their ability to influence through plus I effect will decrease. Thereby, with increasing the electronegativity, Nr3 plus will have greater than NH3 plus. So the second option is also incorrect. The first one is also incorrect. Third one, the relative order of basic strength in aqueous solution. In aqueous solution, when you have ammonia, methylamine, dimethylamine, and trimethylamine, what will be the order? Actually, you have two different possible conditions, guys. When R is equal to methyl, R is not equal to methyl. I'll give you a very simple trick. When R is equal to methyl, it is a smaller alkyl group. Smaller alkyl group, smaller number. That is secondary greater than primary greater than tertiary. When R is not equal to methyl, larger alkyl group. The larger alkyl group has to be a larger number. It is secondary greater than tertiary greater than primary. Smaller alkyl group is 213, larger alkyl group is 231. In aqueous solutions, it does not depend only on inductive effect, it do depends on solvation ability. That is, solvation happens through hydrogen bonding. If you take tertiary amines, there is no hydrogen atom over there. You have only the lone pair. Okay. So ability to involve in hydrogen bonding will be less. But if it is secondary, it can have hydrogen bonding stability, but it will also have inductive effect. Tertiary, it is stabilized through only inductive effect. But when it is primary, inductive effect is less, but hydrogen bonding is more. So here cation stability is driven by both the factors, that is through inductive effect as well as hydrogen bonding. And the best part is the secondary alkyl group, which is stabilized by both factors. That is the reason whether alkyl is methyl or not equal to methyl, we have the secondary first. And what order did he mention? Is tertiary amine more, followed by secondary, followed by primary, and ammonia. This is very much incorrect. So the last option, none of these. All the three relations are incorrect. So the last one is none of these, and that is the correct answer for this question. So how did you find this, students? In a single question, we had a concept based on nucleophilicity, another one is minus I power, another based on the basic strength. Right? Let's move to the next one. This is the last question, a very, very important and a very simple concept. Among the following orbital interactions which represents hyperconjugation interaction. Hyperconjugation, hyper, excess conjugation. Earlier conjugation was restricted to pi system only and lone pair positive. Later on, two scientists named Becker and Nathan have suggested that even the sigma electrons can also involve in a concept called as no bond resonance, and later on it has been changed to hyperconjugation. So hyperconjugation can happen when you have a sp2 carbon. Along with the sp2 carbon, you should also have a sp3 carbon, at least having one alpha hydrogen. One CH bond is must. So where can you have sp2 carbon? sp2 carbon can be possible with carbon-carbon double bond or with a radical. So let us see, even with carbocation also you can have sp2 carbon. It's asking you to check among the following orbital interactions which represents hyperconjugation interaction. So this is sp2 CH2 plus, this is sp3. So this is very much applicable for hyperconjugation, right? See the next one, free radical. Yes, sp2 and this is sp3. So this is also very well inverse with hyperconjugation. And third one, this is benzene ring, guys. Benzene ring. Can benzene involve in hyperconjugation? No. Why? There is no sp3 carbon only. And the last one is nothing but the pi bonded system with a positive charge. So it is something like this, CH2 plus CH double bond CH2. So this is also sp2, this is also sp2, this is also sp2. So do you think it will involve? No. So many questions, students, indirectly have been asked based upon the type of the orbitals involving in hyperconjugation. So guys, how did you find this series? I hope you have thoroughly enjoyed these questions. Next series is the last series. Next series, that is GOC series 5, will be the last one, and I will try to take up the relatively integer based questions, so where we can have multiple questions of round up. So for the general organic chemistry, I am completing the series with 5 series, right? That's all from my end, students. Signing off, your favorite teacher, Sripati. Take care. Goodbye.
Hello everyone, my name is Madhur Bhatt and I am a BSMS student in ISER Kolkata studying chemistry and working in the field of organometallic chemistry, and I will be an upcoming student in the University of Minnesota for a PhD program in chemistry. I have been a student of Dilip sir during my 11th and 12th standard in Mustif and Aryan High School, and I would like to say that Dilip sir is an excellent teacher for all the different fields of chemistry, that is inorganic, organic and physical chemistry, and his way of teaching organic chemistry is really amazing. He explains each and every reaction and each and every concept very clearly, and the notes that he has given are so useful and so much in detail that I still use them, and it helps me whenever I am in a doubt and to clear basic concepts. So thank you.